finding the volume of solids, and in particular we're going to look at volumes of solids that have circular cross sections. So let's just draw a random shape up here. There's y equals function x. So if I was to rotate this curve around the x-axis between these 2 points A and B, well, the way I think about it, and this is actually how we used to approach it in extension 2, but it's still good to look at this idea to see where it all comes from. I can think of just rotating a slice. So there's my slice, and I'm saying its thickness is whatever the change in the x value is. Now if I was to rotate that slice, I'd get a cylinder or a disc, and its thickness is still delta x. Now the radius of that slice would be the y value of that particular function at any point, and that will equal function x. Now, because I'm going to assume that that thickness is going to get very, very close to 0, I can assume this is a cylinder. And obviously if I made it wide, it wouldn't be a cylinder because the sides wouldn't be straight, it'd be coming out at an angle. Well, we know the area of just the face of that is a circle, so pi times the radius squared, so pi times function x squared. So if I want to know the change in the volume as I'm going along, well, I'd multiply the area of the face times the thickness, which I've said is whatever the change in the x is. If I was to then add up all of those slices, I would get the volume of the whole shape. And so I've got the sum going from A to B, but I'm using limits, because remember I'm saying I want that thickness to be approaching 0, because then it will become something that's exact and not an approximation. It might be squared and it might be pi now, but really, if you think back to how we started integration, this is no different. Because integration, we summed up all the rectangles. Well, it was still just some function we were summing up. And so that's all we're doing here. It's exactly the same as we saw when we were finding area. So yeah, this does become the integral, but not of the function, but of the function squared. And that will find us volume. That kind of makes sense because of the area being in units squared, whereas volume being in units cubed. So we've multiplied it by another dimension. And if you think about it this way, if you think of dx being the thickness, so that would have a unit, and then function x has a unit, and we units squared, we end up with units cubed, if you like. So here's another random curve. What we're saying is, if I want to rotate from A to B, and we end up with some interesting shape, maybe it's one of those things your mum puts flowers in and sticks on the dining room table. What do they call them? That's the word. Vase, vase, whatever it is. We could now work out the volume of that if we know the function of the curve. So the volume of the solid of revolution, we call it. So we're revolving the function. If we're going about the x-axis, it would be pi times the integral of whatever the y value is squared, dx. And how do you remember that? Well, if we're going around the x-axis, then it's dx. We could, of course, rotate around the y-axis if we wanted to, but then it would become the y, because we're going around the y-axis. But we'd also need to use the y values, and it would become x squared that would be integrating. Let's now create some formulas that we know, and you've just accepted to be true. So the formula for a cone. If I want to create a cone, all I've got to do is rotate a straight line. For convenience, I've made it go through the origin, so it's y equals mx. If I was to rotate that around the x-axis, we would end up with a cone. There it is, a little net diagram of that rotation. So I want to go pi times the integral of y squared dx. Well, y is mx, so it becomes m squared x squared. Add 1 to the power over the power, sub in the h, sub in the 0, and we get the formula for a cone, just not how you recognise it. But that is the formula for the volume of a cone, 1/3 pi m squared h cubed. M, of course, is the slope of the line. So how do we get it into the form that we recognise? Well, it is, as I say, the slope of the line. Slope we know is rise over run. Well, the rise is the radius of the cone, and the run is the height of the cone. So the slope is r over h. Sub that in, and now we get the formula that's familiar to us, 1/3 pi r squared h. So whereas before you just blindly accepted to be true because you have complete trust in your maths teachers, which is a good thing, we now can prove it to be true. Let's do the sphere. So for the sphere, I'm just going to get a circle and rotate it round. And there's our net diagram of that shape. Well, actually, it's probably not the circle that I'm rotating, it's more the semicircle that I'm rotating. I'm taking advantage of symmetry, so you'll notice I've got 2 pi and I'm going from 0 to r. Integrate that, remember r is a constant, it's the radius, so we get r squared x minus a third x cubed. Substitute in r, substitute in 0, this one drops out a little bit nicer than the cone. There it is, 4/3 pi r cubed. Let's do the shape known as, or I won't say its name yet, see if you know the name. Find the volume of the solid that generated when y equals x squared is rotated, well it says revolved, but around the y-axis between 0 and 1. So here is our parabola, just giving you a hint here, here is our parabola. We rotate it around and we get a paraboloid. Yes, it's a paraboloid. Pi times the integral, this time it's x squared to y, because we're going around the y-axis. X squared is y, so we're going to integrate y to y. Y to y, because we're going around the y-axis. 0 to 1, substitute in, and there is our answer. Units cubed, of course, because we're talking about a volume. So pi on 2 units cubed. The shaded region, so that triangle there, we're going to rotate about the x-axis. So what do we get? Well, be careful, this one plays tricks with your eyes. Is it pointing out? Is it pointing in? Is it pointing out? Is it pointing in? But essentially, we've got this cylindrical shape and the cone has been drilled out of it, if you like. Try and get your head around that one when you look at that shape. But just like we saw with area, it's the same deal with volume. If you're going between 2 curves, it's the top one minus the bottom one. But we square it before we subtract, because it's the volume of the top one minus the volume of the bottom one. So in this one, I'm going to be going 5 squared minus 5x squared. 25 minus 25x squared. Add 1 to the power over the power, substitute in 1, substitute in 0, we have our answer. But that brings up another point. Just like with area, we have formulas that we know and can use. So actually, integration here probably was not the best way of doing it. Remember what I said? Essentially, we've got a cylinder with a cone drilled out. So I could have said, well, it's the cylinder, pi r squared h, minus the cone, 1/3 pi r squared h. So I've got 2/3 pi r squared h. Substitute in the radius, substitute in the height, and I get the answer. Remember, where integration becomes useful is when we're trying to find volumes and areas of shapes we don't have formulas for. And then we use integration to create a formula that we can use. If we already have one, then it's more efficient to use the one we already have. Okay, 2005 HSC question. We have 2, they're both parabolas? Yeah, they're both parabolas. One concave up, one concave down. The area in between we're going to find. Remember I said it used to be 2 units, so you'll notice it came from the advanced HSC. And because it was 2 unit, the first question becomes a very easy question. Find the points of intersection of the 2 curves. All right, we solve them simultaneously. We get x is plus or minus 2, and I will concede this is where I made a mistake if I remember correctly. Because I was thinking about the question, like the overall logical question, rather than what they asked. And it did say find the points of intersection, and I just found one of them there because that was the shaded area. But really they wanted the other one as well, which would be minus 2 for. Right, so this shaded region between those curves and the y-axis is rotated about the y-axis. They're giving us a big hint by splitting the shaded region into 2 parts, or otherwise, find the volume. Okay, so there's the picture. Splitting the shaded region into 2 parts. There's my attempt at getting the diagram. What is it, like an Easter egg or something, isn't it? That's what we're finding a volume of here. Well, I know I'm going to find the integral of x squared to y. But the thing is, again, with area, same as with area, if the boundaries change, then we split it up. So if I'm going around the y-axis, I've got the concave down curve to the axis, but then it changes to be the concave up curve to the axis. So I've got 2 separate things. So is this what they're talking about when they say splitting it into 2 parts? Let's put a line there. That's where I'm splitting it. it. Now, I want to know what x squared is equal to, because we're going to go x squared to y. First one, nice and easy, that one there, y equals x squared, we got it already. The second one, I'd rewrite it and I get a 6 minus half y. So it's going to be these two added together. Add 1 to the power over the power, sub in the numbers, and eventually we get our answer, 24 pi units cubed. So they've now put it into the Extension 1 course, so you've got to expect they're going to up the level a little bit from a 2-unit question. So here was the one from last year. We're going to rotate this trig curve, but going between 0 and x equals pi on 2k. We just don't know what k is. Some number bigger than 0 though. Find the value of k for which the volume ends up being pi squared. Well, I'm going around the x-axis. So it's pi times, will be k plus 1 squared, sine squared kx. K plus 1 squared. K is just a constant number, isn't it? So I should be able to factorise the k plus 1 squared out. That's not part of the integration. So I'm really just integrating the sine squared, and I guess that's where they've turned it into an Extension 1 question, because now we have to use our technique for doing the square of sine. And sine squared, using our double angle, I can rewrite that to be a half of 1 minus cos double angle, so 2kx. So that becomes x minus 1 on 2k sine 2x, substituting in pi on 2k to 0, and we end up with pi squared k plus 1 squared on 4k. What was the question again? We wanted the volume to be pi squared. We have to find the value of k. So we're not finished. We now have to solve this equaling pi squared. So the volume is pi squared. Well, the pi squareds nicely cancel. So k plus 1 squared is 4k. We get k is 1. K is 1 for that one. All right here. So volume.